Hello students, welcome back to our discussion on the application of the principles that we have learnt on the topic of electrochemical equilibrium, and we are going to look at some more numerical problems in this topic. In particular, in today's lecture I am going to discuss how one can determine the solubility product of a sparingly soluble salt. Experimentally, there are many different methods which you can employ to determine the solubility product, but in today's lecture we will see some numbers regarding how to use electrochemical methods to determine the solubility product. So, here comes the first problem. It requires you to calculate the solubility of silver chloride in water, where the solubility will be expressed in the molality scale at 298 Kelvin. And as I have already mentioned, we are going to use an electrochemical method. But before we proceed any further, let us have a look at the equilibrium that this particular solubility of silver chloride in water describes. So, what I have is I have silver chloride solid. This, when put in water, partially dissociates into silver plus aqueous plus Cl minus aqueous. And since it is a sparingly soluble salt in water, I have mentioned that this dissociation is not complete, and therefore, in an equilibrium mixture you not only have the Ag plus ion and the Cl minus ion in water, but you also have some undissociated silver chloride solid. Now, if I want to use an electrochemical method to determine the equilibrium constant associated with this solubility equilibrium, obviously the first step would be to design a cell in which I will the net cell reaction will be having silver chloride solid giving you silver Ag plus aqueous plus Cl minus aqueous. Now, let me propose the following cell that would reproduce the solubility equilibrium as the net cell reaction. So, what I have is this. I have two compartments. In one compartment, that is the one on the left hand side, I have a solid silver rod dipped in an aqueous solution of, let us say, silver Ag plus, some containing Ag plus ion. Then there is a salt bridge connecting it to the right hand side compartment, where I have an HCl aqueous solution as the electrolyte solution, in which I have dipped in a rod which contains silver wire and a silver chloride solid paste on it. Now, how do I know that this cell would reproduce my solubility equilibrium? Therefore, what I would do is I would check this by writing out the half cell reactions and the standard reduction potential. So, what you see is the reaction for the half cell reaction for the electrode on the right, that is silver chloride solid taking up in 1 mole of electron giving you 1 mole of silver solid and releasing 1 mole of chloride ion in the aqueous medium. So, the standard reduction potential of the electrode on the right is 0.22 volt. Now, if I look at the other half cell, there in the notation of reduction I have Ag plus aqueous taking up 1 electron giving you silver solid, and from the data table it is known that the standard reduction potential of the redox pair that I am using on the left hand side, that is plus 0.80 volt. So, what I will do is I will write down the net cell reaction in the usual way, and the net cell reaction now gives me AgCl solid plus silver solid which is coming from the second half cell reaction, giving rise to Ag plus aqueous plus Ag solid, which is coming from the first half cell reaction, plus Cl minus aqueous. And therefore, in the more conventional way, where we do not really worry about whether silver is being deposited on the two electrodes, I will write down the net chemical equilibrium as AgCl solid going over to Ag plus aqueous plus Cl minus aqueous, thereby giving me an equilibrium situation which is the same as that of the solubility equilibrium established in solution for silver chloride in water. So, this is the only trick part for this particular problem, but there is something that you should worry about. You see that E naught L is 0.80, which is higher than the standard reduction potential E naught R of the electrode that I am using on the right. Therefore, left to themselves, this electrochemical cell will not spontaneously drive electricity through an external circuit. Rather, you have to supply energy or electrical power from outside to drive a current through this particular cell. But that is not exactly our lookout here. Our lookout is, does this cell, in whichever way it runs, produce the solubility equilibrium? And as I have said, it does. Let us now go back and look at the definition of equilibrium constant. And what I know is the equilibrium constant for this solubility equilibrium will be given by activity of Ag plus ion in the aqueous medium multiplied by activity of the Cl minus ion in the aqueous medium. But here that is not going to help me too much. Rather, since I am employing the electrochemical methods, I will be using the definition that the natural logarithm of Ks, that is the equilibrium constant for the solubility equilibrium, would be equal to Nf by RT multiplied by the standard cell potential of the electrochemical cell that I am using over here. So, this is the working formula that I need to employ. Now, let us go ahead and try and understand that in this case, for on the right hand side, I need to know the number of electrons transferred for the net cell reaction, and we have seen that N is equal to 1. Since I am talking about knowing the solubility at room temperature, therefore, I know the value of RT by F. So, what is the next value that I need to find out from here? That must be E naught cell. So, let us have a look at the half cell reactions and the standard reduction potential as before and find out the standard cell potential. And the standard cell potential is E naught cell equal to E naught R minus E naught L. So, by the given values, I find that E naught cell is equal to minus 0.58 volt. Before I proceed, I would like to mention that E naught cell is related to minus Nf E naught cell is related to delta G naught reaction, that is the standard reaction Gibbs energy. So, if E naught cell is negative, that means that the standard Gibbs reaction Gibbs energy is positive. That is what tells me that the way I have constructed the cell, I will not have a spontaneous electrochemical equilibrium. Rather, I will have to work from outside by passing electric current, so that this equilibrium is established, and that is why I said that all I am interested here is the solubility equilibrium and not how that particular cell works. Okay, coming back to the solution of this simple problem. Now, I know that I am going to find out natural logarithm of Ks, that is the equilibrium constant for the solubility equilibrium, in terms of n, which is known, in terms of E naught cell, which is known, and since I am working at 298 Kelvin, I can actually put in the values of F, R and T equal to 298 Kelvin along with n equal to 1 and E naught cell equal to minus 0.58. Now, what does it give me? That gives me the logarithm of Ks equal to minus 22.59, and that eventually means that Ks is equal to 1.55 into 10 to the power of minus 10. Please note that here Ks is a dimensionless quantity. That is because everywhere I am using the activity of each of the species present in the equilibrium mixture. As a result, my equilibrium constant is going to be a dimensionless quantity. But I understand that this Ks is nothing but activity of Ag plus and activity of Cl minus, as I have mentioned before. Therefore, I would say that if I use the fact that this is a sparingly soluble salt, only very small amounts of Ag plus and Cl minus will be present in the aqueous solution, which means that I can replace each of these activities by their molar concentration. So, how many moles of Ag plus ion is present per kg of water? That is S, if S is the solubility of AgCl. Similarly, the number of moles of Cl minus present in the aqueous solution is again S. Therefore, I get this result that Ks, that is the solubility product of AgCl, that is equal to S square. Now, I know the numerical value of solubility product, that gives me that S is equal to nearly 1.24 into 10 to the power of minus 5. Now, I would like to highlight the fact that I have got a numerical value, but look at the question. I want solubility S in moles per kg of water. So, what I am going to do is, I am going to remind myself that the S that I am using here is actually in the molality scale, where S is a number, small s is a number and S naught is in the molality scale. So, that is 1 moles per kg. Therefore, whatever I have obtained here is actually the solubility of silver chloride in moles per kg. So, if anybody asks you at the end of the exercise, what is the solubility of silver chloride? You must be able to say that the solubility is 1.24 into 10 to the power of minus 5 moles at 298 Kelvin, and that is a very small number, which is characteristic of any sparingly soluble salt in water. Now, what we are going to do is, we are going to look at a second problem, again based on the solubility, but in this case we are not going to be limited to a single temperature, rather we are going to look at the temperature dependence of solubility. Okay. So, now let us see that hydrogen and carbon monoxide gases have been tested for use in fuel cells. And where are these fuel cells going to be used? These are expected to power spacecrafts. Now, whenever you are putting something in a cell, you have to worry about whether you can dissolve the in this case gases in some kind of a molten salt mixture. So, what people did was, they tested the solubility of these two gases in molten sodium nitrate potassium nitrate mixture, and the experimental data was fitted to an equation which looks like this. So, for example, for the hydrogen gas, it was found that the logarithm to the base 10 of the solubility S of hydrogen gas in the molten salt mixture is linear with 1 by T, where the intercept is minus 5.39 and the slope is minus 768 Kelvin, where temperature is expressed in the units of Kelvin. So, this must be a very nice experimental setup which can handle a large variation of temperature at very high temperatures also, and that gives you a linear fit of the solubility data to 1 by T. Similarly, you get a linear fit of the solubility data of carbon monoxide in the molten salt mixture, and here once again you see some other value of the intercept and some other value of the slope. The question is, can I find out the standard molar enthalpies of solution, that is delta reaction H naught for the two gases at 570 Kelvin? So, while doing this problem, I have explained to you why it is a problem that combines the concept of electrochemistry and chemical equilibrium. It is just that these values have been obtained in a fuel cell while building a fuel cell. So, here I note several important things. I first note that for either of the gases, we are using the following equation to describe the temperature dependence of the solubility of the gas. So, log to the base 10 solubility, that is equal to A plus B by T, where T is in the units of Kelvin. Since I am taking a log to the base 10, you must understand that S must be a dimensionless quantity. It must have been defined with respect to some S naught. So, that also tells me A must be a dimensionless quantity. So, what is going to be B? B actually, if I look at the slope over here, that is slope of the straight line where my x axis is 1 by T, I find that this is minus 768 Kelvin for hydrogen and minus 980 Kelvin for carbon dioxide. So, that is the first point that I note, and I understand that I will have to use this expression to find out the standard molar enthalpies of solution. Now, whenever I am talking about molar enthalpies of solution, I understand that the underlying chemical equilibrium that I am talking about is something like this. So, if I have any gas A at 1 bar pressure say, and if I dissolve it in a solution which gives me this A solution, then I understand that the equilibrium constant corresponding to this equilibrium is S by S naught divided by P by P naught. Now, this is going to be equal to S. This equilibrium constant is going to be equal to S because I am using the gas at the standard state. So, I understand that in this case I am using S naught as 1 mole per cc per bar and P naught I am using as 1 bar. So, S is given in the experiment to be in this particular unit. Okay. Now, moving ahead, therefore, I have to understand that I can use the Van 't Hoff equation, which goes like this, that if I take a derivative with respect to temperature of the quantity ln K, I should be able to find out the standard molar enthalpy of the reaction solution, but this would be divided by R T square. Now, this basically says that I should be able to find out delta H reaction, delta H naught reaction, provided I know how ln K varies with temperature. Now, what do I have here? I have K equal to S, and what do I know further? I know that because of this equality and the experimental data that I have with me, so log to the base 10 K, that must be equal to A plus B by T. So, there is a way by which I can look at the temperature dependence of K, but please remember that for Van 't Hoff's equation to be correct, I have to take a natural logarithm of K, but my experimental data is in the log to the base 10 K. So, what I will do is to evaluate d ln K dt, I will still use this equation, but what I will do is I will start with it and multiply on both sides by this number 2.303. So, the left hand side of this equation becomes this, and what happens to the right hand side? The right hand side, of course, both the terms are now multiplied by 2.303. So, the net outcome of this trivial algebraic exercise is that now I know what natural logarithm of K is. So, I find that I have converted my experimental data, and it now gives me ln K equal to 2.303 A plus 2.303 B divided by T. And please remember, I know the values of A and B from my original fitting data. Okay. So, this is where I will go ahead, because I know ln K, I will find out d ln K dt. So, if I take a derivative of the right hand side, obviously the first term does not contribute, because there is no temperature term there, dependent term there. So, what is the outcome of taking a temperature derivative of the second term? So, the constant terms will come out, because as you see B is a constant depending on which gas you have. So, it is a characteristic constant, it does not depend on temperature. So, I will have to know d dt of 1 by T. That immediately tells me that d ln K dt, that is equal to minus 2.303 B divided by T square. So, now I am going to combine this result and compare it with the Van 't Hoff's equation, and immediately I can say that delta H naught reaction by R T square, that must be equal to the quantity that I have obtained here. And on algebraic simplification, therefore, I find that the standard molar enthalpy of solution will be minus 2.303 multiplied by the universal gas constant R multiplied by the characteristic constant B of the gas. Please remember that although I am using the notation A and B for the gas, these are no way related to the van der Waals constant. These are arbitrary characteristic constants that I have used for this particular problem. Okay. So, moving ahead, what do I have? I have, for the given gases, the standard molar enthalpy of solution is this, where I know the characteristic constant B for hydrogen and the same for carbon monoxide. So, what I will do is I will write it out for hydrogen. So, the standard molar enthalpy of solution is going to be minus 2.303 into the standard value of R multiplied by the value of B for hydrogen. And if you do the evaluation, you will find that the standard molar enthalpy of solution is going to be 14.70 kilojoule per mole. If I go ahead and repeat this calculation for carbon monoxide, so the first part remains the same, it is minus 2.303 into 8.314 joule per Kelvin per mole, but now it is multiplied by minus 980 Kelvin, giving you the standard molar enthalpy of solution for carbon monoxide as plus 18.76 kilojoule per mole. So, now what you have is this. This was the problem that you had at hand. You wanted to fabricate fuel cells by dissolving either hydrogen gas or carbon monoxide gas in a molten salt mixture comprised of sodium nitrate and potassium nitrate. And then you found the temperature dependent values of solubility from your experiments, and then you wanted to know what is going to be the standard molar enthalpy of solution for each of the dissolving these gases at 570 Kelvin. And from our calculation, what I find is that the standard molar enthalpy, if I use these two equations, these are independent of temperature. So, it does not matter whether I am employing 570 Kelvin or 600 Kelvin, their values are going to be plus 14.7 kilojoules per mole, and carbon dioxide is going to be plus 18.76 kilojoules per mole. And you must also note that this dissolution process under standard pressure of 1 bar is going to be, in both cases they are going to be endothermic processes. So, this brings us to the end of this lecture, where we have showed how electrochemical cells can be used to determine the solubility of a sparingly soluble salt, and how such values of solubility can be employed to practical applications by combining the concepts of electrochemistry and those which we have learned in chemical equilibrium. Thank you.